Hi everyone. Today we have another session of the GOCC. We have Eline Mannino from University of Oslo, and they'll be talking about the rank nullity ring of matroid. Before we continue, we go over the guidelines for GOCC. We are all learning. Everyone has something to contribute, and no one has all the answers. And with that in mind, Eline, take it away.
Okay, thank you. Thank you for having me to this meeting. My name is Eline and I use she, her as a pronoun. I'm a new PhD student at the University of Oslo, and Chris Chow is my supervisor here. And what I'm talking about today is the rank nullity ring of a matroid. And this is a new object that we are defining in a project that I'm working with with Felipe, Rincón, and Fife from the University of the Queen Mary University of London. And so just stop me anytime for any questions or comments, or if you see any mistakes, please also let me know. Okay, so the plan for today is that I will briefly give a background on matroid theory. You've probably seen it before, but I will go through. I will try to go through it briefly. Then I will introduce a new object, which is something that we call the rank nullity ring of a matroid. And I will give some motivation for defining and studying this ring. I will tell you a few properties of the ring, and I will propose some further questions and research directions. Okay, so matroids are an abstraction of the notion of independence in mathematics, in several branches of mathematics, and they were independently discovered by the Japanese mathematician Takeo Nakazawa and the American mathematician Hassler Whitney in the 1930s. And there are many ways of defining matroids, but for the purpose of this talk, I will define them in terms of a rank function. So a matroid on a ground set E of rank D is a function on the power set of E to Z that has to satisfy that it's non-negative and bounded by its cardinality. It is monotone, which means that if S is a subset of U, then the rank of S is less than or equal to the rank of U. And if we take S and U as two different subsets, then the rank of their union plus the rank of their intersection is less than or equal to the rank of S plus the rank of U. And the rank of the whole set is equal to D. So if we take as a ground set this vector configuration on the left, and as a rank function, the dimension of the span of some given vectors, then this is a matroid. And also, if we look at this graph on the right-hand side and define as a ground set the edges of this graph, and as a rank function, the size of the spanning tree of the spanning forest of some given edges, then this is also an example of a matroid. In fact, these two are different representation of the same matroid. Another way of thinking about matroids is in terms of hyperplane arrangements. And hyperplane arrangements are in fact dual to vector configurations. So on a hyperplane arrangement, we can define a rank function which returns the codimension of the intersection of some given hyperplanes. So here I have drawn a line arrangement consisting of 4 lines, And this line arrangement defines a matroid of rank 3 on 4 elements. That is because if we take the intersection of all the lines, the intersection is empty, and the codimension of the empty set in the plane is defined to be 3. So even if we like to think about matroids geometrically, and a lot of the motivation and intuition comes from geometry and graph theory, in 2016, Nelson proved that 0% of all matroids are representable. So by representable, I mean that we can represent them as a vector configuration or a hyperplane arrangement. And what this means is that when n goes to infinity, then the number of matroids that arise in this way, so from a hyperplane arrangement, compared to all matroids that are not necessarily representable, like as a vector configuration over any field, goes to 0. Yeah, so this is the first example of a matroid which is defined purely combinatorially, which is called the uniform matroid. So the uniform matroid of rank D on a ground set E of size n is the rank function returning the cardinality of the subset if the cardinality is less than D, so the rank of the matroid, and D otherwise. So if the uniform matroid can be represented as a hyperplane arrangement in general position, which means that the hyperplanes have to intersect nicely. So, for example, in the case of line arrangements, no more than 2 lines can intersect in the same point. And we call U and N, so the uniform matroid of rank N on N elements, the free matroid. So another important definition are the flats of the matroid. And a flat is a subset of E, which is closed on the rank. So this means that the rank of the subset increases every time you add an element to the subset which is not already in there. Flats are ordered by inclusion. So we can make a lattice that is called the lattice of flat of the matroid. So here we have the same line arrangement as before. And on the right-hand side, we have the corresponding lattice of flats. So here on the bottom, we have the ranks. We have the flats of rank 0, which is only the empty set, because like the empty set corresponds to like no hyperplanes intersecting. So the dimension of the space itself is 0. Then the rank of the one-dimensional set of the subsets of size 1, sorry, are like this flats here corresponding to lines. So these are of rank 1 because lines have codimension 1. Then these subsets here are the flats of rank 2 because they correspond to points. So they have codimension 2. And finally, the whole set has, as before, empty intersection. So the rank is 3. So as I tried to illustrate now, when the matroid is representable, then the flats they correspond to linear subspaces of our hyperplane arrangement. Okay, and so to a matroid, we can associate a graded polynomial ring, which is called the Chow ring of a matroid. And this was introduced by Feischner and Jusvinsky in 2003. And it is defined purely combinatorially. So for each flat, each non-empty flat in the lattice of flats gives us a generator. Moreover, this polynomial ring is modeled out by two relations. One linear relation, where we, for every element of the ground set E, we are summing all variables corresponding to flats containing that element I. And we have also a quadratic relation. So we get xf times xg every time that f and g are flats that are incomparable, which means that neither f is contained in g nor g in f. So in general, the Chow ring of a variety in algebraic geometry is a well-studied ring which encodes the intersection properties of that variety. And in fact, when the matroid is realizable, so we can represent it as a hyperplane arrangement, we can associate a nice and smooth variety to that hyperplane arrangement, which is called the Cauchy-Procesi wonderful model of the hyperplane arrangement. And Jusvinsky and Feischner proved that the Chow ring of a matroid, which is defined purely combinatorially, is in fact isomorphic to the Chow ring of this wonderful model of the hyperplane arrangement. Okay, so now I can finally introduce this new ring that we have called the ranked nullity ring of a matroid. So let me briefly introduce one last thing, which is the nullity, which is, yeah, sorry. Okay, so the nullity of a subset, this equals to the cardinality of the subset minus the rank of the subset. And remember also that the Chow ring of the free matroids, so U and N, this is the polynomial ring generated by variables corresponding to flats of the matroid, but in the free matroid, all the subsets are flats. So I will just denote it by XS for S a subset of E. And then we have the usual relations, I plus J. Okay. So the ranked nullity ring of a matroid M with rank function R on a ground set of N elements is a subring of the Chow ring of the free matroid of rank N on N elements, which is generated by variables Y, I, J, which are sums of variables corresponding to subsets having the same rank and the same nullity in the matroid. So I would be the index which is taking care of the ranks of the flats. So so I will be bounded below by 0. So 0 is obtained only if the matroid has a loop, so a subset of size 1 of rank 0, and bounded above by the rank of the matroid. Whereas J is bounded below by 0. And so remember, this is the nullity, so cardinality minus rank. So this happens only every time that a subset has full rank. So the cardinality equals the rank, and it's bounded above by the number of elements of the ground set. And then their sum must be bounded above, minus the rank, and bounded above by the size of the ground set. Okay, so what is worth noticing here is that the rank nullity ring of the matroid is a subring of the Chow ring of the free matroid, so it is inheriting lots of relations. Moreover, whereas the Chow ring of the free matroid is like when n increases, it gets huge. So because we have one generator for each subset, so this means that we have 2 to the n number of generators. So this number increases exponentially. Whereas this rank nullity ring is much smaller, and it actually increases only quadratically. Okay. Are you hanging in? Or yeah?
So I have a couple questions. First, the second I is a J under the sum, right? Null of S equals I.
Yes, sorry. Yes, this should be a...
Yeah. And second, what would so if you do this in the Chow ring of M, not of U and N, does this come out any different?
Yeah, it would be different. We haven't looked at it yet.
Interesting.
Yeah, I will explain why it is this subring we're looking at soon. So I will now do an example so we can get a little bit more used to thinking about this ring. So here we have the usual matroid of rank 3 on 4 elements, and the rank nullity ring of this matroid is a subring of the Chow ring of the free matroid of rank 4 on 4 elements. So the first question would be, okay, for what pairs of I and J do we have some variable Yij? And we immediately see that there are no sets of size 1 of rank 0, no loops. So I will never be 0. So at least we know that. So the first we define would then be this one here, Y10, which is the sum of all the subset of all variable corresponding to subsets of size 1. Then we see that we do not have any Y11 either, because there are no subsets of size 2 of rank 1. All the subsets of size 2 are of rank 2, and we can see it here that we are summing all of them. Then we get one lonely guy here, which is the Y21, so one subset of rank 2 of size 3. And the rest of the subsets of size 3 have rank 3, nullity 0. So they end up in this sum here. And finally, the whole set E has rank 3 and nullity 1. Yeah, so this is also a lonely guy. Okay. Yeah, did it help? Okay, good.
Yeah, there's a question-ish. So it's the way of counting all kinds of incidences between these subspaces, like all the ways they intersect. Is that?
Yes. Yes.
Sorry, if you want to clarify, you can ask.
Yeah. So we're looking at all, like we are looking at all subsets now, not only the flats. Yeah. Yeah. Do you? Yeah. Okay. Good. Okay. So now I'll try to explain a little bit of why we ended up defining this ring and why we're interested in it. And for me, the story started when I was working on my master thesis, where I defined and studied some matroid environments called the Chern numbers of matroids. And this now I turn it into an article. So if someone is interested, there is a preprint on archive. And so, okay, so the Chern numbers of a matroid are weights that we obtain when intersecting the appropriate CSM cycles of the matroid to get something that is zero-dimensional. Okay. So what are these Chern? So these CSM cycles, it stands for, it's an abbreviation for Chern, Schwarz, McPherson cycles of the matroids. And first of all, let me say that to a matroid, so to a matroid M, again, this is a rank D on a ground set of n elements, we can associate a rational polyhedral fan, which is called the Ardila Cleveland's fan. So this is also known as the Bergman fan of the matroids. Yeah, that you probably maybe heard of before. And this, so that we denote by sigma m, and it has dimension d minus 1, and it lives in Rn minus 1. Okay, then these k-dimensional CSM cycles that were introduced by De Medrano, Rincón, and Chow in 2019. These are the k-dimensional subfans of the Ardila Cleveland's fan. So they consist of all the k-dimensional cones of the fan. And they have some weights assigned given some combinatorial rule. So each k-dimensional cone will get a weight. So it's like the k-dimensional CSM cycles are both this like k subfans with the weights. This way of giving the weights, they fulfill something called the balancing condition. And in fact, these CSM cycles, they live in something called the ring of Minkowski weights. Of the fan. So star M. Like, yeah. Where here that consists of all k-dimensional subfans with all the ways that we can assign weights, fulfilling some certain balancing condition. And the product here is defined by some certain intersection product. Okay, so what do we have here? It's this is the Ardila Cleveland fan for the uniform matroid of rank 3 on 4 elements. So it is a 2-dimensional fan living in R3. And we can assign, so the zero-dimensional CSM cycle would then be the vertex of the fan with weight 1. Then the one-dimensional CSM cycle of the fan consists of all the rays, and they have rank. They have weight, sorry, not rank, but weight -1 if these are the rays that are spanning the two-dimensional cones. And if they are in the middle of a two-dimensional cone, then they just get weight 0. And then they have weight 1 on all the top-dimensional cones. So all the two-dimensional cones, and so on. Yeah. Okay. So back to these Chern numbers. So to a matroid M of rank 3, I can associate 2 Chern numbers. And I index them by codimension. So we get C2 bar of M, so the second Chern number of the matroid, which will then be the weight of the zero-dimensional CSM cycle of the matroid. Oh, there is not so much space, but yeah, you see it. Then we get C1 squared of M, and this would be the weight that we obtain when we intersect the one-dimensional CSM cycle with itself. Yeah. And then to a matroid M. So and this is it, like for matroid of rank 3. I'm just gonna get the light up again. There. Okay, so then to a matroid of rank 4, I get 3 Chern numbers. So C3 of M, which again is the weight of the zero-dimensional CSM cycle. I get C1, C2 bar. So this is the two-dimensional CSM cycle intersected with the one-dimensional CSM cycle. And finally, I get C1 cube of M, which is the weight that I obtain when I intersect the two-dimensional CSM cycle with itself 3 times. Okay, so this intersection product inside the fan can be quite hard to compute. So it's not that easy to compute these Chern numbers directly, but luckily there is another way that we can do it, because in 2018, Adiplacito, Ha, and Katz proved this very beautiful isomorphism, which says that the ring of Minkowski weights is isomorphic to the Chow ring of a matroid. And this means that the CSM cycles that live in the Minkowski weights ring, they live naturally also here in the Chow ring. So they correspond to a homogeneous polynomial of degree d minus k. So be careful here about the indexing, which is, yeah. Here we count codimension and here we count dimension. And so a question is, okay, how can we represent these CSM cycles in the Chow ring? Because then a problem of intersecting subfans is reduced to computing products of polynomials, which is much easier. And while I was working on my master thesis, then Felipe Rincón and Fife were working on exactly this problem here. So how to go from the CSM cycles to the Chow ring. And by doing a lot of computations, they came up with a conjecture for how to represent them. But they were only able to give proofs in some specific cases. So they weren't able to give a nice proof before this paper came out, which is called the tautological Chern classes of matroids by Berget, Spink, Tseng, and in 2023. So they introduced this tautological subbundle of a matroid, and they are geometric models inspired from the realizable case. And they showed that these bundles, so we have the tautological subbundle of M and a tautological quotient bundle of M, that they have some very universal properties. So which means that a lot of other matroid invariants are specialization of these bundles. So they prove that the Chern classes of these tautological bundles, they live in the, so here, like maybe here your question maybe makes more sense, that they prove that they live in the Chow, in the Chow ring of the free matroid. So that's why we're looking at a subring of the free matroid, of the Chow ring of the free matroid. And the most important result for us in that paper is this theorem below, which says that we can express the CSM cycles in terms of these bundles, or one of the bundles, the tautological subbundle of the matroid. And multiplying with this guy here, which is called the Bergman class of M, the main effect of this is to remove everything that is not a flat. So in fact, we were able to find an even more general formula. So not only for the CSM cycles, but for the Chern classes of the tautological subbundle of M, and also, in fact, for the Chern class of the tautological quotient bundle of M. And then the formula for the k-dimensional CSM cycle just came by deleting everything that is not a flat. Okay, so here we have it, our formula. The tautological Chern classes of a matroid are given by this formula here. And so alpha S, this is a function of the chain of subsets. So here we're summing over all chain of subsets. And here the sum of the exponents must be equal to K when we're looking at the K Chern class of the tautological subbundle. Okay, and then and the coefficients are given by this are just a function of the ranks of the subset and the multiplicity. So we see that the coefficients do not really care about what subset they are. They only care about the ranks and the multiplicities. So this means that this formula is very symmetric. Like every time we have subsets having the same multiplicity and same ranks, they will have the exact same coefficient. And this is why we came up with this rank nullity ring. So corollary, we proved that the Chern classes of these tautological bundles, they live in the rank nullity ring of the matroid. And the formula for the Chern class of the tautological quotient bundle of the matroid is exactly the same as the one here, but the only difference that is instead of having ranks here, we have the nullity of the subsets. Yeah, and so the main maybe observation to prove this theorem is that, okay, recall what these variables so the fact that this in fact that these formulas can be expressed in terms of the yi's. So let's remember what the yij are. So we are summing over all subsets having the same rank I and the same nullity j. Then every time that we take an S and a T of the same sum, then they will have the same rank and they will have the same cardinality. And this will imply that S and T are incomparable. And remember that one of the relation of the Chow ring says that then this again implies that XS and XT equals to 0. So a lot of terms just disappear when we, so it means that we can, every time that we have an exponent here, we can put an exponent directly in here. And this is like the main observation that makes us rewrite this long sum as a sum in terms of the yi's instead. Yeah. Okay, so I don't think I will go through this slide, but the proof of this formula that we find is mainly computational by result that we find in the paper about the tautological bundles of the matroid. So it's mostly just computational proof. Okay, so let me see. Just about. Oh, I didn't take the time, but I have until 7, right?
You have about 10-15 minutes. That's fine.
Okay. I'm not checking the chat, by the way. Are you freshman dream for matroids? Okay, nice.
Yeah, we are monitoring the chat, so don't worry.
Okay.
If there's an important question, we will just tell you.
Okay, great. Okay, so now I will tell you a little bit about what we know about this rank nullity ring of the matroid. So let us recall that an automorphism of a matroid M is any permutation of the ground set elements such that it doesn't change the rank of the subset when we apply a permutation. So for example, if we go back to this matroid here, that's our favorite matroid, then we see that the only elements that we can permute here without changing the rank is the elements 1, 3, 2. So the ones intersecting in this point here. Yeah, does it make sense? Yeah. And so, in fact, so the automorphism group of the matroid would then be the symmetric group on 3 elements. The symmetry, yeah. And note also that the automorphism group of the uniform matroid of any rank on a subset of size n would be the symmetric group on n elements. Okay, so proposition. So the rank nullity ring of a matroid is invariant under the action of the group of automorphism of the matroid. But why don't we have this inclusion the other way, right? So For example, we see that the element x0, lives in here because we're only permuting the elements 1, 2, 3. But it is not an element of this ring here. So it's just a subring of the ring invariant under the automorphism group of the matroid. Whereas for the uniform matroid, we have this equality. So the rank nullity ring of the uniform matroid is the ring of invariance under the action of the automorphism group of the matroid on the Chow ring of the free matroid. Okay. So the Chow ring of a matroid, it's a well-studied ring, and it satisfies some nice properties that were proven by Adiprasito and Katz in 2018. And like it satisfies the Poincaré duality, which means that the degree I part of the Chow ring is isomorphic to the degree D minus I part of the Chow ring of the matroid. And if we say that HI is the dimension of the degree I part of the Chow ring, so what I mean is the number of basis elements of this of the degree I part, then this means that HI is equal to HD minus I. So if we put all the HIs in a vector, then we will get a symmetric vector. So this is what you can see on the right-hand side of the table. Here I have computed the H values for the Chow ring of the free matroid. So yeah, not a very interesting example, but you see that it's symmetric. Then the Chow ring of a matroid also satisfies the hard-Lefschetz theorem, and this implies unimodality, which means that these H numbers, they will increase up to a certain point, and then they will decrease. Yeah. And finally, they satisfy the Hodge-Riemann relations that imply log concavity. So this means that HK minus 1 times HK plus 1 equals HK squared. Okay, so then a natural question is, does the rank nullity ring satisfy any of these properties? And we see immediately by these examples down here, which are, so on the left side of the table here, we have the H values for the rank nullity ring of the matroid. And so when we look at this H vectors down here, so corresponding to matroids that are not the uniform matroid, we see immediately that they are not symmetric, so they will not satisfy the Poincaré duality. But for these few examples here, they are both unimodal and log concave. So, could it be unimodal and log concave? Good question. We see also that here this vector has some really nice binomial coefficient. So this is also a good question. Can we prove something about it? And we did. So the first thing that we noticed is that the rank nullity ring of the uniform matroid does not depend on the rank D, but only on the set. So we can already see by these computations that it looks, you can see that it like U35 is the same as U15, for example. And so, yeah, I don't know if I will show you, I don't know, does it make sense? But yeah, okay, good. And then we were also able to prove that we found a basis for the rank nullity ring, and this is in fact the exact, so we deduced it from the rank, from the basis of the Chow ring of the matroid, which was already proven in the first Jusvinsky and Feichner paper about the Chow ring of the matroid. So this is just, we're just summing basis elements in the same way as before, and we prove that it is a basis. Yeah, and then we're counting how many basis elements there are to prove that the this H vector consists of these numbers here. So these binomial coefficients here. Yeah. Then we were also able to prove that the rank nullity ring of a matroid on n elements is strictly increasing up to the ceiling of n divided by 2. So we have half the part of unimodality, but we have still not proven the decreasing part. So this is still a question, whether it's unimodal. And we have neither proven that it's log concave, but we want to try to do so. So other further investigation questions we have is that these tautological classes of matroids, they prove that they have some really nice deletion contraction properties. So could there be that also our ring has some nice deletion contraction properties? And then further on, I would also like to continue studying Chern numbers of matroids, because during my thesis, I was only able to prove things for matroids of rank 3. So I gave a combinatorial formula for computing them, and I also found some bounds on both the Chern numbers and also their ratio, and found some very nice connection to geometry and line arrangements. But I haven't done much in higher ranks. So this is also something I would really love to work on. And so if any of you wants to join, that would be cool. And yeah, I think that was it. Thank you.
Awesome. Let's thank Eline for a wonderful talk.
Thank you for listening.
So, do you know anything about the basis in the general case?
The basis, what the basis of the matroid is?
Of the rank nullity ring. Do you have a basis for? Do you have the basis of the rank nullity ring in general?
No, we don't have it.
Mm-hmm. Do the numbers look explainable in some way? The dimensions? Okay, too many of these are uniform, I guess.
I don't know. They do inherit some tendency from the Chow ring in general, since they have this increasing form. But I don't know. I don't know yet. Still very fresh, this stuff. So yeah.
Interesting.
Yeah. I had a similar question. If you could explain maybe the direct products using the known binomial something, like any of the binomial coefficients could explain what the direct sum of is. for uniform matrix.
In which
It's in case of rank nullity.
in which slide you mean?
So the slide, so for example, if you look at like the direct sum of two uniform matrices,
Oh
does
yeah.
it follow at all from like the binomial coefficients, like the previous single ones?
Okay, like you mean these examples down here?
Yeah, like do they follow from anything above? Can you say, I don't know,
Mm,
add some numbers or
I don't know. I haven't. I don't know. Do you see some pattern?
no, that's what I was asking. Maybe if you looked
Yeah,
at it.
I don't know yet.
Yeah. Yeah, I don't know. Maybe.
No,
Yeah,
I
I
haven't
don't know how the
yet
how the
thought that
direct sum works. Yeah.
Yeah, no, I haven't like thought about it so much yet. But it's probably like it would probably be a good way of starting to like think about these specific examples and then see if we can generalize something.
I guess
Yeah.
the question that kind of goes with that is, have you plugged the stranger numbers into the OEIS?
Into
The Online Encyclopedia of Integer Sequences, the OEIS.
yeah.
It is the online tool for, I've come up with a bunch of numbers in a sequence. I want to see if anyone else has ever seen these numbers before.
Oh, okay. Oh, I don't know what it is.
Yeah, it is a very useful website. I'll just
Oh, okay. Did you put it on the chat?
Prairie
Just put it in the chat.
Yeah.
Yeah.
Oh, great.
Yeah, so
Okay. Yeah, nice.
easier with things that are indexed by one number, but even if you have a sequence of lists of numbers, like it handles
Okay, cool.
numbers, well, yeah.
Okay, nice. So it just okay tells you, oh, this is the same as this one, and
Right. So, in research, you come up with, like, oh, I find that the dimension of my, series of rings increases like this. And you're like, oh, that sure looks like some numbers. And so you just throw it into the OEIS. And so when 5 years later, someone else comes up with that exact string of numbers, they can just stare at it and go, why?
cool.
Yeah, just like for an example, if you plug in the non-Fano one, you
Yeah.
get this, which is apparently, if you read the Pascal's triangle, the 1, 2 Pascal triangle, which is also called the Lucas triangle, but if you read it by rows, you get those values. So it's
Oh,
in some combinatorial object somewhere.
okay.
Like if just to if you haven't done
Okay.
that before, then yeah.
Okay. That is cool.
Mhm.
Yeah. Okay. So you
Yeah.
completed that one.
So you can just put in your numbers and
Okay. Wow. This I can't wait to try this out.
It is a very fun and this is a surprisingly useful tool for combinatorics.
yeah.
It has led me to at least 2 connections I had not thought to look for.
Okay. Cool. Like I don't have a background in much background in combinatorics, so
Yep.
it's cool to know then.
Do we have any other questions for Lena? Okay, then let's thank the speaker again.
Okay, thank you.
Then we'll stop the recording.